This conference will now be recorded.
I'll be mostly focusing on like whichever very relevant and like frequently asked. Okay. So we can go ahead with something like I will ask some question like you can tell the answer in few lines. So then I will go through like detailed explanation of that question. Okay. And I mean whichever is like very simple and like frequently which you all already you might know, I'll not prefer, but like whichever like mostly relevant for FPGA discussion, I will start discussing on. One thing, first question I would like to discuss, give some example of non-synthesizable constructs. Okay, so or like what is the difference between synthesizable and non-synthesizable constructs. Can you give me some example of synthesizable and non-synthesizable constructs?
Synthesizable announcements like we can realize implement using gates.
Right. Any code what you write in Verilog, which is like can be implemented in the FPGA or in ASIC, that will be synthesizable construct, right? So can you give me some examples which are not synthesizable?
Joint and flow and like hash functions, delay, including a delay in the main
Right.
program.
So you might have written in the initial begin whatever like for initialization and all in the test bench, right? Initial begin, you will write set of code and then end. So this whatever is there inside the initial begin, that basically we write for test bench purpose, like hash delay. We'll give hash 10 millisecond delay in the test benches, right? Those are just used for implementation of like simulations, basically for the simulations. But for example, if you want to implement that 10 millisecond delay inside the FPGA, how do you do? So these are the frequently, I mean, when we ask the questions, right? That way we frame uh, the consecutive questions. So we will ask like which are synthesizable. They will say that like delay 10 millisecond, all these are non-synthesizable. But in FPGA, we may need that delay, right? So if I want 10 millisecond delay, can you tell me how you are going to achieve that? How you are going to achieve a 10
Using a
millisecond?
counter.
Right. So we should know what is the clock coming in. So for example, if 40 megahertz clock is coming as the input, okay. So now internally, how do you, so can we use this clock directly? We can use, but there will be like, what is the issue actually? I mean, if I use 40 megahertz, like this is an external crystal, you have external crystal. So from there, like you are getting 40 megahertz. So this is my scenario. So can you suggest me how you are going to handle this clock and generate 10 millisecond delay? I have 40 megahertz clock. Can I use that 40 megahertz clock directly?
No, sir.
Yes. How we are going to handle that? we may put clock generator. I mean, either, I mean, you can see if you want 40 megahertz itself also, it's always recommended to use PLLs, right? We have MMCMs, and through that multi-mode clocking manager. So through that, you can generate 40 mega itself. Like, let me consider like you have generated 40 mega clock, right? So can you tell me how you are going to write a logic for this, for generating the 10 millisecond delay? You mentioned counter, so can you just tell me like how you are going to write that logic? Forever and all will not work actually. That is also non-synthesizable constraint. Forever. That is for simulation only we use that clock generation, right? Forever.
One always delay which has to maintain a delay of 10 milliseconds. Next, we need to go for a functional block of what actually design.
Always, can you tell me always?
Always at positive clock edge and go for a counter. Counter has to count for a 10 milliseconds for a
Okay.
particular.
So counter, I'll be keep incrementing. Counter equals to counter plus 1, right? So how do I know that like it reached 10 millisecond?
When counter value, we need to compare with an highest count. If that count is reached, if else statement we need to use. If the count value
Yes. So
reached
what
to
you
then
are
particular.
okay? If count equals to what is the value I have to compare?
That value.
See, actually, 40 megahertz clock is coming, right? So every positive edge, your counter is incrementing. So what is the duration of this clock? 1 by 40 mega, right? So how much it is? Can someone compute and tell me in microsecond? What is 1 by 40 mega? It is, I think, 0.25 into 10 power minus 7. That means 2.5 microsecond. Am I right? One count takes 2.5 microsecond. You have to see how many counts required to reach 10 millisecond. That means 10 millisecond divided by 2.5 microsecond. How much it is?
Four milliseconds.
Not millisecond. So it is actually 2.5 by 10 is 4 into 10 power minus 3 into 10 power 6. So 4 into 10 power 3, correct? So that is 4000. 4000 is the count which is required, right? Now, whenever my count is 4000, it means actually it reached 10 milliseconds, right? Now I got to know it is like whenever count is 4000, my count is 10 milliseconds. Can you tell me what should be the bit size of this counter? What should be the size of this counter? Bit width, whether 5 bit, whether it should be 12 bit or 16 bit.
5-bit, I think.
5 bit can go up to 32, right? 2 to the power 5, that is 32. 0 to 32, but I want counter should go up to 4000.
12-bit counter, sir. 12-bit counter.
How did you find? Basically, we have to always, whenever you want to find how many bit required to reach that value, you have to take log to the base 2 of that value. Log to the base 2, 4000. How much it is? How much? It's 12 bit actually. It takes around 11 point something, but basically we have to round it to the higher value, that is 12 bit. We cannot have 11.5 bit and all, right?
So find log 2.
So if you want to find the bits, right, it is basically we take the log to the base 2. Okay, so log to the base 2 of that number will give me how many bits required to represent any value. Basically it is in this way, right? So 2 to the power, so for example, now 2 to the power x is the maximum value I can get. Like for example, 4096. So this is x is basically number of bits, right? So if I want to represent this, if I want to find this x now, so what I have to do? Both the side I have to take log to the base 2 power x equals to log to the base 2 4096. So this, it is basically x log 2 to the base 2. This will go, it is 1. So x equals to log to the base 2 of 4096. Agree?
Yes, sir.
Yes, sir.
So this way, usually in interview we keep building the question. So I mean, we will start at some point and we will reach to this level. I mean, we keep digging. I mean, here also we have like further we can dig, but like let's stop at this point. Now next question, you write if some condition, else if some condition, so on. Else you will write some condition, right? So this is one statement. I will also write case statement, case A, case B, and default. So if someone asks you to design the circuit for these different scenarios, can you tell me what kind of circuitry it will be inferred in the FPGA for if else statement and case statement?
If else is a D flip-flop.
Not really. I mean, you can assume in case of combinational also you can have if else. D flip flop will come into picture. So
Multiplexer?
if you want to infer a D flip flop, then I can just have this, right? Always at pause edge of clock. Then if I say D equals to A and okay, D equals to A and B, I will mention. This is one statement. I will have another statement assign D equals to A and B. So if I draw a circuit for this, this will be just simple AND gate. Now if I draw the circuit for this with like inside that always block, then it will be one AND gate
And
followed by
along with the D flip flop.
D flip flop. This is the circuit. But in the case of if else and like case statement, what it will be inferred.
In if else it will inform multiplexer.
Both the cases kind of multiplexer will be inferred, but there is a difference between those two actions, case and if else.
Case multiplexer is used for case statement, sir. Because
In if
depending
else
on the select
also
lines
kind
and
of multiplexing, yeah. If else also kind of multiplexer will be used actually. So here it is basically priority encoder. Okay, if you see here, it based on like whichever comes first, it will be executed. It has to ignore other things, right? When if, then else, then else. In this case, it is kind of priority encoder. So you will have one condition. So this expression 1, if I say, so here it is expression 1. Then here you will get the output, and so this input, right? So if it is 0 or 1, so finally you will have expression 2 here. This expression 2 again it will be coming from another mux. Okay, so this mux, right, selection line will be again depends on some boolean expression. So see this output, right, here expression 1, expression 2, what I'm saying, that is inside this expression 1, expression 2. So these are conditions actually. The select lines will be conditions. So if this condition is corresponds to this select line, so next it will be this select line, so on. So it basically these conditions depends on that it will select the line. But in case of case statement, right, so this is actually priority encoder. But in case of case statement, it is purely you will have select line and all the possible expression. Expression 1, expression 2, expression 3. So here if it is case 0, 1, 2, 3, in that way you write, right? So that will be here. It is connected to select line. So you can say case will be inferred as multiplexer, whereas if else statement will be inferred as what circuitry? What circuitry I said?
priority encoder.
Priority encoder. Okay. Corresponding to this Verilog itself, few of the things you can note down, you can explore. Okay, so you can let me know if you are like not in that. You can find this answer. I mean, straightforward. You can mostly in most of the interviews you expect explain case Z in Verilog. That like I have seen in my own experience, like I have seen like in many interviews they ask case Z. Okay, you can note down this so you can explore this later. Case Z. Why the tasks are used in Verilog? Tasks. It is like not a synthesizable constraint. Okay, so usually they'll ask the difference between task and function. So task is something like only simulatable. It cannot be synthesizable, especially we use for bus function model creations and all. Okay, so it is a sequential circuitry. I mean, like you can have a clock and all in the task. Whereas function is a synthesizable, but this function cannot be used for sequential logics. For instance, if you want to create one multiplexer, if you want to create some gates, then we use tasks. Not tasks, functions. Okay, so the difference between task and function is very important. Mealy and Moore machine, the FSM type that they ask. Blocking and non-blocking. Okay. Now, we might have seen like maybe in Jan or Feb, I don't remember. So, in the second class or third class, we discussed something like slice L and slice M in FPGA. Do you remember what is the difference between these two?
Slice L is for a logic, only logic can be implemented. Slice M is used for a memory implementation as well as logic.
Very good. So memory and logic, and one more logic is there. What is that? One more circuit we can implement.
Shift register.
Right, SRLs. So one LUT can implement any bit shift register. One slice you can consider. I mean, no need of one LUT. You can tell me one slice can implement how many bit shift register?
4 shift registers.
No, how many bits? 4
32
LUTs are
bits.
there. That's right. One LUT can implement 32 bit. I agree. 64. I mean, actually, one LUT will have how many bits actually? How many bits it can store? One LUT can store
6 input LUT.
128 bits.
64 bits. 6 input, right? That 5 input can store 32 bit. Like 6 bit, since it is a 6 input LUT, it can store 64. One slice can store 256 bits, right? But as a shift register, it can use only 128 bit out of that. So in one slice, we can use make it 128 bit LUT.
Also in one CLB, there are more slice cell compared to slice cell, right?
I mean, actually, in CLB, it's not like more slice L. In CLB, we will have 2 slices. Okay. Uh, so, out of that, CLB also, it's of 2 types. We can have slice CLB LL. Whenever I say CLB LL, both the slices are slice L. If I say CLB LM, one slice is L type, one slice is M type. So depends on what kind of FPGA you are using, which series of FPGA you are using. The proportion of the CLB LL and CLB LM we might have.
But why it's like why say slice cell are more compared to slice cell? Like what's the reason behind it?
Because actually we need more logics, right? I mean, the basic purpose of the LUT is to create logics. So using the memory or like using the SRL may be like limited. I mean, we will not have entire LUT as a memory or LUT as a shift register itself, because if I keep that LUT as a shift register or LUT as a LM, right? So slice LM, slice M, it requires more resources basically to make it work like a memory or make it work like a shift register. In a design, you may hardly have only few shift registers, right? Mostly you will be having logics, correct? So for that purpose, we need more logics. Memories or shift registers may be limited. I mean, we will not have much. So that's where like they have given more importance to the slice L, where we need some logics. Memories and shift registers are limited, right? How many shift register you can have? Like whole FPGA itself, we will not have shift registers. Huh? Whole FPGA will not have memories. So I mean, if you have some big circuitry for storing some configuration, you may have like small memory for that. So that's where like we have limited slice M.
Oh, okay, sir.
Next question: what do you mean by differential signal? Why do we need it? Have you heard about differential signaling?
No, sir. I don't know about it.
So especially whenever we get the clocks and high speed signal like DDR or Ethernet. So the configuration will be this way, right? You will have one FPGA and you will have, let me consider you have Ethernet 5. So between these, if you want to interface, so this might be running at gigabits per second. And you know, more the speed, the voltage level will be very less, like 0.9, like less than 1 volts, right? So if I transmit like this, so if I get some noise added, so this data will be, some bits will be corrupted. So what we do, we transmit again like in another line, not of that. Wherever high is there, low. Wherever low is there, high. This way. So you know, always noise we call it as additive white Gaussian noise. That adds up, right? Both the channels will added with same noise. So at the receiver end, what I do, I take the difference between these two. A, if it is A, and this is B, A, B. So since it is like A minus, if I do A minus B, minus of minus, that will plus. So this will be amplified. Whatever the noise is there, right, that get eliminated. So this technique we usually call it as differential signaling. Okay, differential signaling. That basically helps us in terms of removing the noise. Okay. So next important question, many a times they will ask, in almost in all the interviews they have asked me. So what is the difference between FPGA and ASIC? When to use which?
FPGA are used for prototyping, and once the functionality is done, then we go for.
Need not be. As you know, like in 5G or like in defense applications or even in the medical high-end products, we do use FPGA as a product also. So prototyping, yeah, I do agree. For the prototyping also FPGA is used. So wherever the time to market is very less and the product is limited number. Okay, so if I consider any medical equipment, so it may be like hardly each medical equipment will be costing in crores, and like number of medical equipment may be a few hundreds, right? Whereas let me consider you want to manufacture one mobile, so the number of mobile which it manufactures, it will be in millions, correct? So wherever the mass production is there, then I go for ASIC. But where the numbers are limited, then I prefer FPGA.
Low volume of applications.
Yes, low volume applications. And nowadays, even for the high-end application, wherever the things are rapidly changing, for example, artificial intelligence, every time they need some upgradability, algorithms will be rapidly evolving, right? So it is not finalized. It's not the final one what we have. So in that scenarios also, we use FPGAs, like now all the accelerators, servers, right? Radars, base stations. We can implement many algorithms flexibly there. Okay. So one advantage here in the FPGA, are you bothering about like backend design, physical design, or like uh, keeping placement, routing, or rigorous STA? No, right? So here we have advantage of saving all this money. If your system is like, or else you assume you want to design one radar, and you have to like go for like lot of uh, physical design, STA. It's like huge cost, right? So whenever you want to have permanent circuitry, then we go for ASIC, high volume, mass volume production. Then we go for ASIC.
So can you please explain again, like when we say FPGA is a reprogrammable device, so how we reprogram the FPGA once we will finish, like once we will complete the design, then what does that mean if it's reprogrammable?
No. So for
Like,
example, now you have Xilinx FPGA, you assume. Okay, you have Z board. Okay. So Z board, you have like you have designed, like let me consider a small design, like you have designed one full ladder. Okay. So now when you program that bit file of full ladder, now your whole FPGA will act like a full ladder, correct?
yes, sir.
Hello.
Yes, sir. Yes,
Yes.
sir.
Now you feel that whatever the circuitry you have loaded, now you don't want to act like a full ladder. You want some ripple carry adder. So what you do? You change the RTL. You generate again bit file, program into FPGA. Now that FPGA will act like a ripple carry adder now, correct?
Okay.
So that's why we call it as a reprogrammable. For instance, ASIC. Now you consider ASIC. Now in ASIC, you did full ladder. Okay. So for that, like all physical design will happen. ASIC is manufactured. That IC comes to you. So now you feel that like you want to make ripple carry order. So what you have to do? So that ASIC you cannot reconfigure because that is already hardcore circuit which is designed by physical design and manufacturing. But here in the same circuitry, same IC, you can keep reprogramming the bit file and you can modify that IC into different functionalities.
So in FPGA, when we write in a design, so we don't like in case of ASIC, we are packaging that to, like we are getting a physical ice for that. And in
Right.
case of FPGA, we are not doing that. We are only generating bit stream for that, right? And
We are generating the bit stream, but we are programming into that FPGA, right? FPGA IC we are programming. But once you program, it is not permanent. Like for example,
okay,
let me just show you.
design.
Let me download some image and show it. If you consider this image, if you see here, so You can see this, whatever it is here in under that heat sink, right? That is FPGA. Now through JTAG there will be JTAG cable, right? You will program this FPGA for your circuitry. So whatever the LED you have connected or like whatever the input you are giving, so this FPGA will act like that circuit. Now later if you want to reprogram through USB or JTAG, you can just reprogram this FPGA and you can make it like that circuitry, and according to that all the hardware will work like that. But in ASIC not like that, right? So this whatever, so in ASIC also this chip might be there, but that chip is, for example, if you say full ladder, that chip will act like full ladder only always. Once you have made that chip as a full ladder, you cannot change it. But here we can change the functionality each time.
So in ASIC, we don't need any bit stream, because I have not
No, in ASIC we generate that Gerbers, right? So it's a after physical design through fabrication we are manufacturing. Here not through fabrication, we are writing through JTAG. We are writing that, so that IC is already fabricated. FPGA IC is already fabricated. Where in that inside that FPGA IC, all the lookup tables, block RAMs, all the memories, all the DSPs are already present. So you are just writing the bit stream to those lookup table, DSPs, or memories, such a way that FPGA will act like a circuit you want. But in ASIC it is not like that. So you are designing the circuit itself.
Okay, sir.
Got it, right?
Yes, sir.
What do you mean by synchronous FIFO and asynchronous FIFO? Why do we need that? Have you heard about synchronous FIFO and asynchronous FIFO?
Same clock pulse we will use in synchronous FIFO.
As in synchronous FIFO, writing and reading will be of both same clock. In asynchronous FIFO, read clock and write clock will not be same. It will be different. Right? Why do we need that? Especially for your CDC application, wherever the timing crossing will be there, right? So there we use it. For instance, you assume now ADC data is coming at 70 mega sample per second. Okay, so here somewhere you might be processing this data at 100 MSPS. So if you directly integrate this, what will happen? This 70 MSPS and 100 MSPS, there is a mismatch, right? So that's where in between we will put block RAMs or FIFOs. So we will store at 70 MSPS. We will have some flag which indicates whether FIFO is full, whether FIFO is empty, whether data is available. Based on that, at 100 MSPS, I will process the data. It can be synchronous or asynchronous. Synchronous, both read and write clock will be same. In asynchronous, write and read clock will be different. Clear? Now we will see some protocols. Can you name some protocols? What you know?
SPI.
How FPGA communicates? FPGA or like FPGA communicates with other ADCs or any ICs?
SPI.
SPI. Okay. What else?
AXI, I2C, and
I2C.
Right. UART also is one of the protocol. Right. So what is the difference between UART, even Ethernet, JESD nowadays, like these high-speed interfaces also there, SerDes. So what is the difference between UART I2C and SPI? UART, is it a asynchronous or synchronous protocol? UART is a asynchronous protocol. The name itself, UART, Universal Asynchronous Receiver and Transmitter. It's a asynchronous protocol. Okay, so here we will not, what is the meaning of asynchronous protocol? Here we do not have clock. We have TX and RX lines. Then how receiver and transmitter will get to know where is the start, where is the end? So usually if you see the format in which we are sending the data, right, one bit will be start bit, and we can send 5 to 9 bits of data and one stop bit will be there. But both the side clock should be same. Both receiver and transmitter should know what is the clock speed. Then only this UART we can send. Okay. So along with this start and stop, in between we will have parity bit. Okay. Then whether I2C is a asynchronous or synchronous?
Synchronous.
It is synchronous. In I2C, we have two lines. One is SCL, that is clock, and one SDA, that is data. So every rising edge of the clock, we will be sending the data. So here also we will have start, stop, acknowledgement, all these things. Okay. So now,
read, write.
yes, read, write also, some address also will be there, right? Slave address also will be there. Now, next question, whether UART is a full duplex, half duplex, or simplex? UART.
Full duplex, I think so.
UART is full duplex because we are transmitting and receiver at the same time, right? Both are happening at the same time. What about I2C?
The half duplex.
Right, it is half duplex because we can send or receive at a, we cannot send and receive at the same time, right? So here we have that only one SDA line. Whenever it is transmitting, it cannot receive. Whenever it is receiving, it cannot transmit. That's a half duplex. What do you mean by SPI? Coming to I2C, so here I2C frame structure is, we will have start 7 to 10 bits and read or write. We will have then acknowledgement 8 bits data again, like that is data frame 1. So 7 to 10 bits is address. Then again acknowledgement might be there. Then finally we will have stop signal. Okay. What do you mean by SPI?
Serial peripheral interface.
Serial peripheral interface. So how many bits are there in that? How many lines are there?
4 lines.
4 lines. What are those 4 lines?
Clock, serial clock,
MOSI,
MOSI,
MISO, and
MISO,
select.
chip select.
Right. Clock, master out, slave in, master in, slave out, and chip select. So whenever chip select goes low, so that chip wherever it is connected, that will get activated, right?
Yes.
Yes.
And master out, slave in, we are sending the data and receiving at the another side. Master out, slave in, and master in, slave out is we are basically receiving the data. Okay. So whether this is a synchronous or asynchronous?
This is synchronous.
Yes, this is synchronous. Synchronous protocol. So what are the disadvantage, advantage of these protocols? You have now all the three protocols. Can you, based on our observation, can you tell me what are the disadvantages, advantages of these protocols?
Maximum speed for SPI is like 10 megabits per second.
Whether in the UART I can go with that speed? No, right? I mean asynchronous. So asynchronous always faster speed is not supported. What about I2C? I2C also it's slightly lesser speed. But what is the advantage with the I2C? We can have only 2 lines. I mean, for example, even if you have 10 slaves, you can manage with 2 lines. But whereas in SPI, as the number of slaves increases, this chip select line will keep on increasing, right? So whenever you have like limited number of pins, then you go with
Different chip
SP,
select.
chips, this I2C, right? Next, coming to the static timing violation.
Hello. So then
Yes, tell me.
SPI protocol, it's a single master multi-slave protocol, right? So
Yes, in
like
I2C
how many
also,
so how
I2C
many slaves?
also, go ahead, go ahead.
No, so you can.
In SPI protocol, right, the maximum slave limited to like number of pins you are having. Okay, in the sense, see, you need for each slave one chip select, right? If you are using 10 slaves, then you need 10 chip selects. So that is the disadvantage. But in I2C, we have that 7-bit, right? So even though that 7-bit, in that like we have some reserved bit, so maximum we can have 1008 slaves. But masters, we can have unlimited masters. But in SPI, only one masters. Actually, ideally unlimited slave you can have. But the issue is that many pins you should have to create the chip selects. Right? That
Each
may not be.
master should have one chip select, right, sir, for SPI?
Yes, yes. Each slave should have one chip select, not masters. Master is only one.
How we design, like we can design that master, no? If we need multiple number of slaves, so we can add multiple number of chip select pin to master. So is there
Yes,
any
yes.
disadvantage of adding number of CS pin to master
There
in
is no
SPI?
disadvantage, but it will impact on your like programming speed, right? Because if you are like operating using single master itself to the multiple slaves, then what will happen, you cannot program all the slaves at a time, right? So you have to like go for like one by one, or like if the same data is there for the multiple slave, then you can make all the slaves as chip select down and you can program in the single shot. But if like all the slaves has to be given with the different data, you have to wait till the first slave is served. So you have to carefully design, like based on your requirement of the speed and like how you have to program.
So then what is the more usable connection, like number of slaves that we can connect?
No, see, the it depends on like how many slaves you have, right? So I mean, when I say it is slave, it means it can be like one 5 ADCs or it can be DACs. So it depends like how many slaves, how many DACs, how many ADCs you have. So for example, let me consider you have 10 ADCs. Okay, so now you want to program that as soon as possible these 10 ADCs. So you may design like parallel multiple SPI masters which will be controlling these slaves, like maybe 3-4 slave at a time. So you have to optimally design like based on your speed requirements. It's a trade-off actually.
So the data rate also same in each slave.
Yeah, it should be same actually,
Data bit.
because master will be giving clock. So based on that master, slave will be working. So slave is not giving clock, right? Master is the one who is giving the clock.
So how we generate clock in master? Like, is there any PLL circuit or?
Yeah. That like SPI circuit you are designing, right? So this SPI, whenever I say, so this is the RTL Verilog code what you are writing in the FPGA. So
Yes.
you will, so for example, this is the SPI block, SPI Verilog block. The input to this is like maybe the data, that 8-bit data what you want to transmit and valid, and some reference clock. If it is like 100 mega here, you want to send like 10 mega. So you might have some clock divider circuitry here, and you will be pushing bit by bit data to through master out slaving. That way, right? You will be designing that. So clock you are generating through PLL or maybe counter or directly exact clock itself you might be giving as our.
So then, what's the minimum frequency that SPI can work? Like also other protocols. What's the minimum frequency that we can use?
There is no requirement of minimum. It can operate at 1 hertz also. But lesser the frequency, it will be very slow, right? There is a limit for higher frequency. Always, you'll have a limit for the higher frequency. Lower, nobody asks. I mean, you can operate at 1 hertz also. Nobody bothers. But is it okay for you? That is the question actually. I mean, that will be very slow, right? Lower frequency, there is no cap. But higher frequency, there will be cap. So, for example, in I2C, standard mode can operate at 100 kbps and it can go up to 3.4 mbps also in the fast mode. And we have some ultra fast mode which can go up to 5 mbps also. That is the cap. But whereas like UART, it can operate, I think, some 80 kilo to 1110 kilobits per second. That's it. And these are the disadvantage. That's where like based on your application and data speed, you will be choosing interface. But many a time, you don't have flexibility to choose the interface. For example, you are choosing one ADC IC which is integrated to your FPGA. So whatever that IC follows, that interface you have to talk to him, right? So that IC designers, what he has chosen, that interface you have to use. So interface is like a communication language, right? So I mean, if that guy knows only Chinese or like only Korean, so somehow we have to translate. I mean, translate the language into Korean, and we have to communicate with him. The same way, if that guy is capable of reading only I2C and you internally you have some SPI, somewhere you should have a translation so that like that guy can understand. So if he is understanding only I2C, then we have to make work like a I2C itself.
So can you also give idea like why we need a protocol for FPGA? What's we need to communicate from FPGA to our design or
Yeah, from our design to ADC or our design to some memory. Like for example, I was saying that like our configuration data is stored in some flash, right? Now, for example, our all the permanent configuration data might have stored in flash. Now, this is your FPGA. If you want to load this flash data to your FPGA, we have something like SPI interface. So through that you will be loading. So it is something like from the external component. So if I bring back the same image, what I shown you previously, like let me just pull back that image. So if I pull back this image, you can see various other components here. Like you have this HDMI controllers, analog controllers, and you will have this DDRs, or you may have some FMC cables. So you might be connecting some PMOD. So if you want your FPGA to talk to them, like for example, you have connected one Wi-Fi PMOD here. So if you want to talk to these guys, so then you need to have some communication protocol, right? That's where like we need that communication protocols to talk to external devices.
so suppose I have this I'm writing one code so that I need to run in FPGA. So for that I also need a protocol, right? Like I will connect all my signals to that interface so that I can
No, it depends on what code you write. What code you are actually planning to write. So all code need not have interface. Okay, so for example, you are internally computing something, and like so through LUD or some computation you are doing, and maybe like where you don't want to communicate with the external IC, then you need no need of interfaces. So if you have any requirement of external ICs, then only that interface is required.
okay, so yeah, okay, so
Okay. Next is basically timing protocols. I mean timing analysis, STA analysis. What do you mean by setup and hold time violation?
so setup time is that like it's a violation where we need the data to, like before the age the launch is we
Yeah, you
need to
assume you have two clocking circuitry, the flip-flops.
capture it. Sorry.
So from here the data is launched and here you are capturing. Okay. So for example, at this rising edge, if you are launching the data, and next rising edge usually you will be capturing at the another flip-flop, right? So what will happen? So whenever this rising edge reaches here, right? So we will have some boundary saying that by that time my data should be arrived, right? But what happens if it arrives after this boundary, then that is a setup violation, because between this path you might have a lot of combinational circuitries, right? Because of that, what will happen? Your setup violation will happen. And after this also, in order to internally latch this data, you will have another boundary here. So till this point you have to keep that data, else what will happen? This data will be lost. So that we call it as hold violation. So hold violation usually we cannot avoid. I mean, like you have to change the architecture itself. But if there is a setup violation, what you can do? What is the method where I can avoid this setup violation?
We can add some blocks, I think. Some
So whatever the
design.
combinational circuitry is there, right? So so basically I have to, so for example, this is like some 10 nanosecond. Okay, here you have setup violation of 3 nanosecond. Then what I can do, I can split this now into 5 nanosecond and 5 nanosecond. That is where I will put one flip flops in between. So now previously, since it was reaching at 10 nanosecond, there is a 3 nanosecond violation. 7 nanosecond still it is allowed, right? But here, since I have 5 nanosecond, so 2 nanosecond still I have some time, right? That is where I avoid this setup violation. So adding this flip flop, usually we call it as pipelining mechanism. Pipelining. Pipelining is the mechanism where I add the flip flops and avoid these delays, avoid these violations. Okay. Okay. So I'll pause for today. So next class we will continue with this timing violation, some of the problems, and after that I will discuss also some high-speed interface related questions, like JESD and some important codes and all. Okay. So any questions if you have, you can ask.
Excuse me, sir.
Please explain that
Hmm.
influence and
Yeah, sure. So if you see this BRAM code, for example, so there are two ways of adding this block RAM. One way using IP catalog, right? So in the IP catalog, how we have to add the block RAM? I have to search VRAM generator. So through this IP, I have to create that component. I have to create this component, and I have to, if I create this component as a IP, then how I have to add to my design? I have to go to the instantiation template, and I have to instantiate this component, right? This is one way of adding the memory. This you are clear, right? How to add the memory. Creating the IP and adding this component as a component in your design. You remember this method?
yes, sir. Yes, sir.
Yes. But if you see here I didn't instantiate this component. What I did, I written a logic such a way that it will infer the memory. If you see here, it has taken 2 block RAMs, right, based on this code. So also I have added some attributes. So this technique, right, adding some attribute and making this to infer the block RAM, I call it as a inferring the memory. So this is the inferring method. Instantiation is like creating some IP and adding those IP in your design. Understood?
Yes, sir.
it is nothing but a forcefully we are placing some block. That is nothing but a inferring, right? Like a
Yes, we are making, we are not forcefully, actually we are writing a code such a way that tool will understand that is like a memory. For example, do you remember if I want to use a lookup table as a shift register, how do we do that? Do you remember the technique what we discussed? If I want to use the shift register instead of flip-flops, usually if you write a shift register logic, it will infer the flip-flops. But how do we make it infer? So in the initial class I had told, wherever you want to infer as a shift register into LUT, what you have to do is you have to avoid reset. If you don't connect the reset, right, it will infer shift register. So we have to, there is actually Xilinx design guidelines. So we have to follow that guidelines and write a code such a way that it will infer in particular manner. So the tool will understand, okay, you are trying to infer this, and according to that he will place and route. Clear?
Yes, sir.
Any other questions?
No, sir. Thank you.
Okay.
Excuse me, sir.
Yes, Kaveri.
Hello.
Yeah, tell me.
Sir, if we know the basic understanding of protocols like I2C and all, is it okay to include such a thing in a resume? Like,
Yeah, definitely.
or
Yes,
else we
yes,
need
you
to
can.
work on it.
Need not be. Need not be.
The basic understanding, the theoretical understanding of such, okay to include
What
in
I
a resume.
recommend, instead of what I recommend is, instead of only theoretical understanding, so I mean, do you have any eval boards?
Evaluation boards, so Vertex 6 is there, sir. Zinc board is
That is
not there.
sufficient for the basic protocols, right? That is sufficient. What you do, you try to run all this interface in the loop back mode. Like, so there are some debug pins, right? For example, you assume you want to test the SPI protocol. What you do, like SPI MOSI and MISO, that slave and master, both you instantiate inside your same FPGA, and through external connection, right, loop it back. I mean, the slave, right, SDSL, you will just connect through wire, short through wire. So what will happen?
Okay.
You can actually test it, right, through signal taps, everything you can test it. So you can say that like you have worked, right? I mean, in the sense like you will be like testing, and you can mention that like you have tested this way and like analyzed and all. So you will get the practical knowledge also. Getting the practical knowledge, we have to create that scenario. That's it. I mean, we can see what you do. I mean, in the company also, when you go to that company, so same protocol you will work, but you can also yourself also you can try that, right? I mean, whether that is working or not.
Okay. Okay. I'll try that.
So that is like self experience. I mean, since you are doing your PhD also, so you can say that like based on the PhD, you are working on that. I mean, certain pieces, I mean, certain optimizations and all, you can work as a part of your PhD also. You have to create that scenarios. That's it.
Okay, sir. Thank you.
Any other things? Okay, then we all meet on next Saturday. Okay. Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Yeah. Thank you. Bye.